In this section, I'm gonna cover the concept map of the whole unit 2. Sorry, this unit is about the ray model of light, and this is the whole mind map I have. So I'm just gonna pause here for a couple seconds. So when we're looking at the ray model of light, we're looking at the light rays, and we could look at the left part first. We usually portray, light rays travel in straight lines, and it is represented by arrows. For arrows, we have real arrows, which is represented by solid arrows. For virtual arrows, we're representing it by dotted arrows. And then we have diverging light rays, parallel light rays, and converging light rays, which means that it is pointing away from the normal point, it never intersects, or it is pointing towards the normal point. And then we could look at the right-hand side, which talks about the light sources. For light sources, we have 4 light sources: the ray source, parallel ray source, point source, and extended source, which this is the meaning of it. And usually it comes from the self-luminous objects or reflective objects. So we could look here about reflection. When light rays changes directions and it encounters objects, it undergoes reflection, and this obeys the law of reflection. This is a little diagram I draw for illustrating the law of reflection, and this is the equation. So it acts on smooth surface and rough surface. For smooth surface, it produces sharp image, and the typical example would be a mirror. And a mirror would be an example for a ray source and parallel ray source. For rough surface, it produces blurry image, and the typical example of it would be a piece of paper. And point source and extended source would be, and a piece of paper would be an example for point source and extended source. So we could look back at here, the central part. When light ray changes directions, when it encounters objects, it undergoes reflection, but when it passes through a medium, then it undergoes refraction. And for refraction, it obeys the law of refraction, and I include a figure diagram for it. And for a refraction, there is dispersion, which is a phenomenon, and I include a problem for it. For both law of reflection and law of refraction, when it combines, there's a special case called the total internal reflection, which there's a problem, but to illustrate for it, and it includes these 2 equations, which is the combination of the law of reflection, and the law of refraction. So when we look at the image formation, we have reflective surface and refractive surface. The reflection side is a bit simpler, so we could look at the mirror, and for mirror, it has plane mirror and curved mirror. For curved mirror, the spherical mirror is the general type, and for spherical mirror, we have thick spherical mirror and thin spherical mirror. For thin spherical mirror, we have the thin mirror equations. And then it could be classified with a convex mirror and a why there's 2 convex? There's one should be concave. Let me change it. So this should be a concave mirror, and the other would be convex mirror. So we're finished with reflection. We could look at refraction. For image formation, it has the refractive surface, and we have plane interface, and we have spherical interface. For plane interface, it would be a bit simpler. For plane interface, we're basically looking at apparent depth. And for spherical interface, where we have only one spherical interface, we have a concave or convex spherical interface. And we're also looking at the apparent depth by this equation. And when we consider that R is infinity, that means that the spherical interface is essentially a plane interface. And that explains why we could look at plane interface with this equation when we assume R is equals to infinity. And this is a little diagram. And this diagram, this thing is convex. When we're looking at 2 spherical interface, we're looking at the lens. And we don't talk about multiple spherical interface in this section. So for lens, we have thick lens and we have thin lens. We could talk about thick lens first. This is the basically how thick lens works. How thick lens work is that this t is with a value. So we have one side and we have another side, two image formations. By the two image formations, we're simply using we're using this equation twice, which gives us this. And when we're looking at thin lens, that t would be essentially very, very small, and we say it equals to 0. Then we could further simplify to have these four equations. And the first one has a name for it. It is called the Lensmaker's equation. So after we look at thin lens, we have converging lenses and diverging lenses. I include both a problem with it. And for converging lens, there's a very, very important example. That is the eyes lens. Our eyes lens are converging lens. And that gives us two phenomena, which is nearsightedness, and it is also called myopia, and farsightedness, it is called hyperopia. And I included two problems for it. So after we look at the concept map, I want to stress a little bit about the aha moments I overcome in this course. The first one is dispersion. It looks a bit complex for me when I start looking at dispersion, but it becomes more simpler after I look at these two diagrams, which talks about how dispersion works when white light travels through a medium, that the red and violet light just spread. So for a given medium, the index of refraction increases as wavelength decreases, and that explains why violet light bends more than red light. The second aha moment is when I encounter spherical mirror. For a spherical mirror, I thought with the thin mirror equation, everything sounds so complex until I realized it is nothing more than the loss of reflection, which we are just looking at this interface, and when light hit this interface, it just reflect to the focal point. The same thing goes with the refractive surface. I first look at it, I feel like it's very complicated until I realized it is nothing more than the law of refraction at this interface. And this is an equation associated with one single refractive interface. And for lenses, this looks so complicated before, but right now it is so simple because it is just using two of these equations. And we're just combining it to give us the Lensmaker's equation. So to conclude, since there is a lot of sign conventions in this chapter, I include a big table for it. And I could explain a little bit for it. For reflective mirrors, we're essentially looking at anything after it reflects. So we're looking at this. We're looking at this side. So everything at this side should be positive after reflection. That explains why concave mirror, when we're doing a reflection, it is converging mirror. So everything should be positive unless the object is placed between the focal point and the mirror. For convex lens, since everything forms behind the mirror, so everything would be negative. And convex lens is a diverging mirror. But the same thing does not apply to refractive surface. Since refractive surface, we're looking at the other side. After it reflects, this should be positive. That is why when we're looking at a concave refractive surface, it is a diverging surface, and everything would go to 0, which is opposite to concave. Which is opposite to reflective. And for convex, everything is positive, except when we're placing the object between the focal length and the mirror, and the refractive surface. This should be a converging surface, it is not a lens. So this is basically the sign convention for both reflective and refractive surfaces. And these equations are the thin mirror or the thin lens equation, and it applies to both. And this is a general statement for magnification, that when magnification is less than 0, the image must be inverted in real. But when the magnification is positive, then the image must be upright and virtual. And that concludes the whole Unit 2.